Cool. Welcome back. Big night for UConn. I don't know if are you sticking around for the chaos that happens at Gamble? Yeah, some. So today, we spent some time working on like module 3 homework and talking about like different methods and stuff. We're gonna build quiz number 3 based on things that we're ready for, things that we think demonstrate what are the important concepts or tools that we built in module 3. So I have note card. I like note cards because like it's about all you need. It's a bar napkin to kind of get started. Like, what is the problem? What kind of forces are there? So I'll hand these out. One side we'll write down like what are the concepts, and then flip it over, figure out what kind of problems. Oh, okay. No. Yeah. What else did we learn, guys? Equations of motion
Smudged my name. I forgot to add acceleration, those that make those.
Yeah, what was different with acceleration equations? Yeah, like polar coordinate. So using like different frames of reference, right? Coordinate systems. Okay. All right. This seems to be coming up a lot, which, yeah, I'm glad we spent so much time on it because that to me, this is like the most important part of this class. Is like, how do I because I feel like, at least when I was engineering student, someone's like, okay, here's the equation of motion, now solve it. And then when I became a grad student, they're like, okay, what is the equation of motion? And I'm like, I don't know. Where do I get that? Where do I even come up with that? I'm like, what? You should be able to find one. And like that, this is where we're finding that, doing that search for that. Then I saw kind of like these ideas of like polar coordinates. I'll call it like inertial. Why were we changing coordinate systems and like creating we had to like redefine what acceleration was. So it seemed like it was more work, right? Or we had to look it up, right? Like if you're in polar coordinates, we have to like, okay, I'm in a polar coordinate system, now I have to describe r and theta, and they're both connected to each other. Why would we do that? Yeah.
Allow us to have like a constant term, either a constant like radius or a constant direction.
Yeah, sometimes there's just stuff that's happening that is constant in maybe a radial direction, or maybe the radius is constant. And we looked at a few different examples, like a spring that's like bouncing around, like a pendulum that is attached to a spring. And so the spring force is always radial, like rather than trying to like figure out what the x and y components are, we can kind of, it creates more work on the front end, but you do less work when you're trying to get to that equation of motion as you're like plugging stuff in. All right, was there other stuff? Or I did see a couple other things. Small angle, okay. Yeah, so small angle, the general term for that is like linearization of most of the time, if there's any kind of rotation in a system, if the angle is changing, you end up with sines and cosines, and if those are part of your equation of motion, one way to simplify that is like linearize the equation, and now everything turns into like sine theta is theta, cosine theta is 1. And the fancy way of saying that is like, I took a Taylor series expansion of this differential equation, and I only use the first order terms. And, yeah. But as engineers, you know, it's like, I was being lazy and I didn't want to deal with any of the nonlinear stuff. So cosine is 1. Pi is 3. And that one's different. That's a different approximation. Good? Other stuff? Yeah.
Maybe like when we shifted the axis to define where the point was and the different set of axes. One was rotated by 3 degrees.
Yeah. So we were dealing with like multiple reference frames and rotations, where like it doesn't always make sense to just say like left, right, X, up, down, Y. Sometimes we need to have rotating. Sometimes we need to like figure out what is a polar reference frame in terms of an actual X, Y. Like if I want to know what the motion of the pendulum is, angle is helpful, but probably I want more like how far left and right is it? So how do I convert that theta and R back into X and Y? Something like that. Yeah, dealing with those multiple reference frames, rotations. And I'm gonna write like up here for this like equations of motion. Like usually we had some kind of constraint on motion, like maybe it was a 2 degree of freedom system, but it had one constraint, like R was constant, or maybe the path was fixed in that when we had the block bouncing on an inclined plane, it has to move along that plane. And yeah. Cool. How does this look? Does it feel like it captures all the work that we put into here? Yeah.
Question. When you make a kinetic diagram as opposed to a free body diagram, what are you supposed to be plotting differently on a kinetic?
For the kinetic versus free body?
Yeah, is it like just essentially where the motion is coming?
So like let's say we've got like all these different forces. I've got gravity, I've got spring force, I've got the thing sliding in a track, so the path is fixed. So it's constrained motion with springs, with gravity, all this stuff. First step is identifying like what coordinate system we want to use here. So maybe, at least when I look at this, maybe I would want to say this is my origin, and then, yeah, how do I want to do it? Well, I should have drawn it on the other side, but that's my R, and this is like, right now it's a negative theta direction. So once I define that, then my kinetic diagram is only describing, so in this case I've got MA theta, and MAR. And it doesn't matter that I have all those other forces and all that stuff. Like I'm just saying this is my polar coordinate system. I guess I kind of drew it weird based on, I just don't like how I drew it, sorry. So I want R down that way and MA theta that way. To say like, if it has centripetal acceleration, it's got to be along that R direction, and then all the other accelerations and perpendicular to that. Yeah, and I didn't draw all the forces on it, but the free body diagram would be all the things causing that acceleration. Does that kind of make sense for like?
Yeah, it's just kind of visualizing the component of force in the theta direction. It's just a little hard to grasp.
Oh, for the forces, or for the acceleration?
Like, if you think of, for example, force in the x direction, you know that x is like horizontal and y is vertical, but we like, I don't really knowing like what direction theta is kind of, it's just a little hard to grasp.
Oh, for theta?
Like MA in the theta direction.
Yeah.
MA in the R direction, I can see that it's like it's along that R. That
Yeah. Yep.
But then theta direction, theta is looks like it's varying, it's changing. It's just
Theta does change, like, because it's, and even R is changing. It's just, it's a little easier to see, like, radial, of like, it's away from my origin. This one's like perpendicular to that direction.
so with MAR is the force like away from origin,
Yeah.
centrifugal.
Yeah, so that would be, like, if you're trying to determine how much centrifugal force I have, then it's going to be that away from, yeah. Yeah. Yeah, thanks for helping. And it probably helped clarify for, like, a lot of people, like, why, how do you determine that, and where are these things pointing? Because it does change, like, and that's the whole thing about these reference frames, is that as the point that you're trying to create this equation of motion moves, the reference frame itself is changing. It makes some things harder, like trying to visualize where these forces are actually pointing, but then it makes the actual math a little bit easier. Because I could just say, like, no, Professor Cooper is nuts. Cartesian coordinate systems all the way. I'm just gonna ignore him and say, this is my acceleration. Now my kinetic diagram for like X and Y coordinates. Is like mx double dot, my double dot. It'll scroll up in a second. And that's also like a perfectly valid equation of motion. In the textbook, it goes through what happens if you do that for a pendulum problem, and you end up with a lot of like jumping, kind of bending over backwards and doing this like trig jump through hoops to get to a final equation of motion.
So the kinetic diagram is kind of just like defining your coordinate system.
Yeah, for the most part, like once you choose a coordinate system, that kinetic diagram has already been written. Like it's already going to be the same thing.
And so like those two components should always be perpendicular to each other when you draw them in the kinetic diagram?
Yep, yeah, because you should always have, like, there are times when you only have one component of acceleration, like if you know the direction is always, if you know there's only whatever an x-axis of acceleration, then it's okay to just draw one, and then you know the other one's 0, or you could draw both and then say 1 is equal to 0. Yeah, but a vector is a vector. Like, no matter what two components you choose for it, it's still going to describe the same exact vector. Yeah, so then over here, I would have like force of the spring. I've got some kind of normal force. I've got mg pointing down, like all sorts of stuff going on there. This one's a little wacky, but. All right, so now we can flip over note card, and next step is figure out like what kind of example or question would, maybe it doesn't cover everything in here, but like some highlights, like what's a way to demonstrate that we understand module 3 concepts and processes. Very different, yeah. Okay. Nice. String mass, right? Yep. Oh, and then how do you approach it? That's my Z. What is that? Oh, for a damped. Okay, yeah. Yep. So then you have spring mass damper. Oh, and then add an FT. Yeah. Nice. Yeah. So far, we've mostly done like 3 unforced motions, at least for us. We can add forces. Nice.
I like the balloon problem. The balloon is so bad.
Yeah.
It's sort of like kind of like a constant radius, but it's being forced.
Yeah.
Not a very complicated equation about it.
Yeah, it ends up being just a pendulum.
Yeah.
Yeah, it's just upside down. Instead of gravity, it's like buoyancy causing it to bounce. Or examples, questions. Okay, all right, good luck.
And like, there's only 2 left. And I have to fill it out with my dad. Because my dad's picking up into another one of my buddies. Yeah, my dad's picking up the driving from side to side. And we have to right as soon as they get to it. I'm gonna bring this to you and everything's gonna help you. And everyone's gonna stop studying. It's not studying. I gotta go. So I don't think my dad's gonna be, my dad's pretty good. Give a 5 course number. No, yeah, it was that I'm working on this that instead of celebrating.
Oh, okay. Yeah. I have no idea, but he said it had 2 periods of freedom. 2 basically. Were you thinking like that applies to anything else, or just? Yeah. Yeah. So like almost like a pendulum, but it's on like a big road. Yeah. So yeah, it's like it starts off big long road, but it's from the outlet and so yeah. My yeah, I think like the pendulum that swings it's something how far will it go as the arm changed. Yeah, you can do it and say like, yeah, R equals some function to make a piece of it either. But okay. Spring mass, like feeling like spring masses, dampers, spring mass damper. Oh my god. Trying to get my screen back. There we go. I think we're back. So, yeah, we talked about like springs, masses. We looked at like springs with friction and looked at equation of motion for that. Oh my god, give me my pen back. There we go. So if we have like a spring, a damper, and a mass, where would you use a system like why would you want something like this?
Like a
Elevator? Elevator door?
shock suspension system on the car.
Shock or suspension? Maybe something like that. What do we think? What does the spring get? So let's say we're designing suspension. What does the spring give you? Oscillation? Do you want oscillation if you're driving a car? Sorry? Flexibility. So now when you hit a bump in the road, the wheel can move, but your car doesn't have to. So spring gives you, the more compliant the spring, the more, also the lower you're gonna drive. But so you need a spring that's strong enough to support the car, but also compliant enough that it can move out of the way. What is a damper giving you? Yeah. So when you go over a bump, because so far what we've looked at is like oscillating systems. It's like once you start somewhere, you're gonna keep swinging back and forth. You'll keep, if we think about it as a pendulum, keeps going left and right. If we think about it as a car bouncing down the road, hit a bump, and I've ridden in a car where the shocks were blown, and we hit a bump in North Carolina. We didn't stop bouncing until South Carolina. Like it's just forever. You're just never stop bouncing. So that's what our springs and dampers give us. Yeah. So it could be something like, it was an old Volvo. So it could be like an old Volvo. Could be mountain bikes and suspension systems, but yeah, most of the time, a good start for designing them is just a block.
Is there a particular like force equation for a damper?
Damper, at least like linear dampers. So we would have, like if I say this I've got mg pointing down. Kx is kind of like, if x down is positive, then for a linear damper, we have B times V. And we do that for two reasons. Like, one, we can design linear dampers. And so if it's a constant, if it's a plunger with a constant cross-sectional area, as it moves through a fluid, it always has B, like the faster it moves, the bigger the force. And it's a nice way to design them. If you get super into damping, then you start looking at nonlinear dampers with like flaps. So you have like dampers with springs on them so that you can get like 2 or 3 different ranges of like B's for different speeds and that kind of stuff.
So it would be just like a constant for the specific damper that you're using?
Yeah, usually it's some kind of constant, and the units end up being like a mass per second, which kind of makes sense for like fluids. It's also like a Newton meter per second, like how much energy you lose per second for a given speed. Yeah, so there's that. There was also, we were looking at an example, like let's say you're watching this car go around the track. You're like sitting there watching the car going around the track. We can describe that in different reference frames. We can say, all right, what am I doing to watch this thing? So I've got some, or wait, let's call this, oh, sorry. So I'm watching this thing at a given angle, and it's some like distance away from me. Or I could think about like, what is the driver actually experiencing? So the driver is going to have some kind of like some acceleration in the forward direction, but then also some kind of v squared over r acceleration in that direction. So you can, and either way you measure it, like it's still got to be the same acceleration once you get to the final value. So that might be one way. So you could compare two different reference frames of like, what did you do as you like watch the car go from 45 or whatever, 135 to 45 degrees? What was the radius? How fast was it moving? Meanwhile, the car's driver was dv dt was something, and v squared over r was like something else. And there we're kind of looking at like how to bounce between different coordinate systems, which was one of the things that we kind of started with too. Are there degrees of freedom in this problem? Like, do we have equations of motion? If we have like a fixed acceleration and a fixed path? What do you think? Let's say the driver's going around let's say the driver accelerates, can't spell. think it'll catch up. There we go. So the driver is going to go around this curve, constant radius. He's increasing speed, 1 meter per second squared. Do we have degrees of freedom here? We have motion, right? We still have motion, but do we have degrees of freedom?
Well, if you can't go the other direction, then I guess there's no real option.
Okay.
I guess he can control how much forward he goes.
Yeah.
Like if he could slow down.
Yep.
Assuming he couldn't go the other direction.
Yeah. And this is kind of a weird concept, but it's like kind of crucial part of what we're exploring here and kind of what we're like learning to navigate is if I give you, or like if you're defining a problem where you're saying, okay, I have to move along this path and my speed is a predefined function of time, which is what happens when you say acceleration is constant. Or even if you say acceleration is some function of time, you just fixed everything. Like everything is now a kinematic constraint, so you're down to 0 degrees of freedom. So there's still like stuff that you can solve for, like there's math that you can do, but there shouldn't be any real like differential equations like to describe a degree of freedom. So we're back to like 0 degrees of freedom. Not to say that this is definitely like part of module 3, but the important part here is like, this is kind of nice because 0 equations of motion, and I just need to solve for changes in coordinate system, kind of back and forth. Was there what else? Sorry, what else? I don't mean to like soak up all the airtime. What else were people thinking about? Oh, pendulum came up a few times. Pendulums. What were you thinking? Like, what kind of things are like pendulum? Like, why would you? Is it just for hypnotizing people? Is that like? Where would you need to understand like a pendulum motion? Sorry? Oh, a clock? Yeah, so like grandfather clock? Yeah, grandmother clock? Is that another one? There's grandfather is like the real big one. I think a grandmother is like a slightly smaller one.
I was thinking of Big Ben.
Big Ben. Does Big Ben have... I think that one's just electronic.
Oh.
I don't think it has a pendulum. Does it?
No, I just thought like...
Yeah. I don't know. You might be right. I don't know. Why do you use a pendulum for a clock? The arms? Just hook the pendulum to the arms so that they bounce? Okay, what keeps it in time? The period of the pendulum. So what was that? What would we figure out was like, did we find the time period of a pendulum? What did we figure out? We found the equation of motion, right? So I'm gonna like, okay. So I'm gonna do a magic arrow. Like, we did some math, but magic, now we have an equation of motion. So theta double dot is now negative g over L sine theta. So how do we control, first off, how fast do we want this thing bouncing or like rocking back and forth for a pendulum? What time period do you want? 2 seconds.
Like between every time it crosses the middle, it's like every 2 seconds.
Okay, so like every, I think,
Could be 4 seconds.
I think it's every, I think you want it to be like, right? Don't you want it 1 second?
Well, yeah, but
One full period to be 1 second, I think.
it just seems very short. You know? It seems like it's going pretty fast.
Yeah, now I can't remember. Anyway, but like some factor of 1 second, right?
Yeah.
So we want things to happen once per second, like cycles per second, 1 cycle per second, or 2, or 1/2, one of those. How do I get there? What do I do? What do I have control over? Can I just change the angle? Like change how big of an angle? Would that change how fast it's moving? Why not? The length of the pendulum, right? Because we have an equation of motion, and no matter what the initial conditions are, for the most part, the solution, again, I'm using another magic arrow. Is it coming? There we go. The solution is going to look something like this, where whatever initial angle I was at, that's my magnitude. Some combination of angle and speed. So what's the time period? How long of a time period do we have? This one's kind of like project, like looking forward, because we'll do this in the project. Not for a clock, but for like general kind of pendulum stuff. We can come back to that. How much time? We only have like 2 minutes left. All right. We'll come back to choosing or figuring out time periods and stuff. But what kind of which one do you feel like ready for, or like that demonstrates knowledge pretty well here? Do you want to like build up equation of motion for springs, dampers, masses, or look at like rotating reference frames or pendulums? Springs, masses, springs and masses. What do we think? Springs, mass. Do you like pendulum? Looking at pendulums? Pendulum. Do you want to look at pendulum with a damper? A little damper on the pendulum? Then you end up with spring, mass, damper solution. No? Not interested? What did we end up with? Oh my god, now I can't. Oh yeah, it was a rotating spring mass system. So the spring mass is moving in a circle at a constant speed. What happens to that thing as it bounces around in a circle? Spring mass damper, maybe? Like something like that? Yes? Any? Alright, so we'll work on like, that'll be like quiz 3 is like build out free body diagram, kinetic diagram, write out equation of motion. Alright, cool. Thanks. Thanks, you too.